For example, you have 2 electrons from hydrogen atom, okay. I don't care that they came from which energy level. They can be any from energy level. And I wanted to write I have 2 electrons, and I wanted to write the wave functions for the state with the minimum energy. How I can distribute 2 electrons in the energy level of hydrogen atom and get the minimum energy. This is the first energy level, and this is the second energy level. I can write it E1, E2 for the hydrogen atom. I have 2 electrons. So one possibility is that one electron seated here with this, and one electron seated here with this opposite spin up and down, flip up and down. There is another possibility that one electron seated here and one electron seated here. The same. Of course, the up here, down here, it doesn't change. And it can be down. For electron up, I write the wave function by Xi1, okay? Xi upper 1, if the electron is 1. If the electron is number 2, you know that how I write it, Xi2. If the electron is down, and this is my first electron, it's stupid to talk about the first or second electron because they are just changed by the one index. So I can write Xi plus for up, Xi minus for the down. Xi is like phi, just wave function. Because for the electrons, talking about the location is useless. So as you mentioned, this X refers mainly to the spin of the electron. So this is the situation which I have. So what is the wave function if I want to write for here? What is the energy here first? For this situation, the energy will be, the total will be 2E1. For example, 2 minus 30.6 electron volts. 27 electrons. What is the wave function? The wave function psi total, of course, the spinel part, because the wave electron has 2 parts in wave function. One is referred to the spin up and down. One is the orbital part. Like this electron comes from which orbital? 1s, 2s, 2p, 3d, different orbitals. So the wave function total for electron, I want to tell you that there is a special part which we call it normally psi L M N cross the spinel part. So for us, the spinel part here is important for us. What is the psi for this case? One is up and one is down. So for here, the spin part, where I can write, sorry, here I write. The spin part for this situation will be one is up, one is down. But this is correct? No. When you change the electron 1 to 2, it doesn't exchange. When you change it 1 to 2, it just becomes plus 2 minus 1. It doesn't have any relation to the previous one. But this is not the one which you can write the wave function. The correct is this. You needed to write with this. So I think this is okay. So this will be the wave function for this singlet space, singlet state, singlet. Because if you calculate the total spin here, the total spin will be 0. That's one of them. For that, I didn't know that. Maybe this state has the minimum energy than that. This is minus 27, so I don't know. Maybe it gives you less. We don't know. Let's see. What's the energy for here? This is actually orbital 1s. This is the orbital 1p. 2p, sorry. 2s, the lowest state. Yes. But if you go to p and this thing, energy will be increased. So energy will be 1 minus 30.6 plus 1 minus 30.6 over 2 over 2 minus 30.6. How much will be that? Approximation will be 123. Look at that. What happened is that it has the lowest energy than that. So if you have a 2 electron and if you want to arrange the system with the lower energy, this is not the best option. This is the best option. This minus 20 because the number is lower, less than that. So what is the wave function for here? Again, the wave function for here will be the spin part. What is the spin part? The spin part will be P1, P2. Do you need to do something more? No. This is yes. Still, the total wave function doesn't have the property of the changing the one minus to the other ones. We talked about the total wave function, yes? Still, we didn't talk about the spatial part, huh? Spatial part. With the spin, you cannot do anything more. You cannot do anything with this. This is the only things which you can have. For a spatial part, you can use the scatter. So I can write body radical 2. Look at that, what I will write. One electron seated here in 1s orbital, huh? Phi 1s electron 1, Phi 1s electron 2, Phi 2s electron 1, Phi 2s electron 2, and you see, if you change x1 to x2, this will be negative. So remember that to keep it the Pauli exclusion principle, it is not very easy just to manage the spin like here. It was fine. You know why it was fine. Both electrons sit in the same state S. So if you want to write the, look at that. Yes? This is the special parts. Because both of them sit in the same energy state. Same wave function. So for that reason I didn't write that. Here the spin part is important to make it this negative after exchange of the particles. So Pauli exclusion, yeah, you see this is hard. It's very hard. Just for 2 electrons we talked about more than 10 minutes. 15 minutes to explain how to write the wave function. Yes? So you needed to both, at the same time you needed to fix 2 things. The total wave function should be negative, I know, after the exchange of the particle for fermion. But we have 2 options. Either checking the spatial part or spin the part. Sometimes you see that, like here, that it is impossible to make the interchange, this minus, extract the minus from a spatial part, because they sit already in the same energy. You need to work on this. And sometimes here, you see that they have the same spin, but they sit in the different state. You never can write that plus 1 minus 2, yes? This is wrong, because they sit in the same spin. Plus, plus or minus, minus. Even minus, minus is okay, if you want. Look at that, no problem. Also here, look. Okay. I mean, the first can be negative, opposite, second being positive, or one can be up and the other one can be anything. You needed to work on the spatial part. So the spatial part comes from the Slater detector. So that was the story for the 2 electrons, 2 fermions. So the difficulty now is that we needed to keep the Pauli exclusion principle for the system with huge number of the particles, huh? N particles. You needed to keep the quantum mechanics for the system with N particles. So to do that, you needed to use the Slater determinant for N particles, huh? In case. Sometimes you needed to put here phi, especially. Sometimes you needed to put phi. Huh? This comes also from the Slater, you see that, yes? This comes from the Slater also. Just replace phi here instead of the phi, and again phi here instead of the phi. 1 and 2, 1 and 2. This comes like that. For the system with N fermion, we have this total wave function. Psi 1 and x1, psi 1 and x2, psi 1 and xn, psi 2 and x1. Look at that. So, of course, you see, I told you, of course, sometimes you use this for the spin parts, and sometimes you use this for the special parts. It depends to your configuration. So, just imagine that. Write the von Neumann statistical mechanics with such wave functions. So it's very, very hard things. I mean, working with the quantum mechanics, same with the large number of the particles, it's very hard. So, now I wanted to back to our statistical mechanics. And as you remember, the first calculation which I asked you to do was I asked you to find the omega E, yes? The number of the state or density of the state, something, and plot that as a function of the total energy. So I told you that it will be like Gaussian always. So E and the omega E, it will be Gaussian around the average of the energy. Like the, remember, I give you number of the particle and 2 or 3 energy level, and I ask you to give me the possibility to have the total energy, for example, this. For each total energy, you have some number of the possibility. So this is the number of the possibility. So number of possibility, sometimes was 0, huh? Sometimes was also 0. Sometimes with some energy it was 0 also. We don't know that. And we explained that this omega is related to the entropy. Later we say that, okay, later, you remember, later we talked about the number of the possibility, as a weight of the each energy state. We call it that S is a KB ln by that. And if you remember, we write it that like ln WNI, and the problem was how to find the WNI. And we propose a method to calculate the WNI. You remember? So now I want to write WNI for the WI or WNI. I don't know, WI is better to write WI. Also here. NI or WNI is the same. What is that? This is the number of the possibilities to distribute some amount of the energy between the different energy level, and each energy level can have some number of the particles. Each energy level can have some number of particles. We call it this by G, GI, occupation number or density of this. I want to tell you that if you have a bosonic gas, so Bose gas, as I told you, each energy state can be occupied by any number of the particles. So if you just think it about each element of the ensemble, like some blood. If you set one particle in one state and the second two particles in second one, it depends. Maximum you have a GI. GI is the maximum number of the particles which you can put in each energy state. You can insert in each energy state. And the total number of the particles is Ni in this. The total number of the particles in this energy level is Ni. So I don't know that, but depends. You know, sometimes we write this as a WNI. So in this case, this is they call it WNI lowercase anyway. Because you know, Wi is the number of the possibility for each energy, and you have a number of the energies, so the total number will be a collection of all of them. So W1, W2, W3, W4. So each possibility should be multiplied to give you the maximum 3. So by the counting method, now we can use the counting method. So by the counting methods for the fermion, this WNI will require Ni plus Gi minus 1 factorial, Ni factorial, Gi minus 1. And this is for boson. For fermion, maybe I will be back to this again in the next lecture, because I want to find an easy way to derive this expression. The easy way is that you use the counting. And you started by lower number of the particles, like 5 particles, 2 energy level, and try to understand that how to write this expression for the any n number of the particle with, and each energy level you put at some number of the particle like G1, G2, G3. This is for boson, and this is that's for fermion. And for classical particles, for Boltzmann particles, Now do you know if you accept that this as the expression for this by the combinational mathematics just, then the next step is that to find the entropy and make the maximum entropy. Yes? Making the maximum. So you write the entropy.